Picture this, an entire star torn apart, its light vanishing as it spirals into an unfathomable darkness. This isn't science fiction. It's happening right now, somewhere in the vast expanse of our universe, where supermassive black holes lurk like silent predators. These cosmic monsters, with masses millions or even billions of times greater than our Sun, defy everything we think we know about space, time, and reality itself. What secrets do these enigmatic voids hold? How do they shape the very fabric of the cosmos around them? And why, despite their destructive power, might they actually be the architects of galaxies like our own? Supermassive black holes aren't just strange, they're the universe's greatest unsolved mysteries. Imagine something so dense that not even light can escape its grip, yet so influential that it dictates the fate of entire galaxies. They're hidden in the hearts of nearly every large galaxy we've observed, including our own Milky Way, yet we've barely scratched the surface of understanding their true nature. Some spin at nearly the speed of light. Others spew jets of energy powerful enough to light up the cosmos for billions of years. And some might not even be black holes at all, but something far stranger. This is where our journey begins. Over the course of this video, we'll unravel 30 of the most mind-bending mysteries surrounding these colossal cosmic anomalies. From the paradoxical way they grow to unimaginable sizes, to the eerie whispers of their gravitational waves, to the chilling possibility that they could be portals to other dimensions, we're diving deep into the unknown. By the end, you'll see the universe in a whole new light, where the rules of physics twist and bend, and where every answer only leads to more questions. So buckle up, the cosmos is about to reveal its darkest, most fascinating secrets. One of the biggest puzzles in astrophysics is how supermassive black holes came to exist in the first place. These cosmic giants didn't just appear, they had to form somehow, and the process defies our basic understanding of time and scale. Take the early universe, for example. We've observed quasars, blazing beacons of light powered by supermassive black holes dating back to when the cosmos was less than 1 billion years old. That shouldn't be possible. If black holes grow by slowly consuming matter over billions of years, how did these titans reach such mind-boggling sizes so quickly? Scientists have two leading theories, and both stretch the limits of what we thought was possible. The first suggests that supermassive black holes were born colossal from the start. Imagine a vast, unstable cloud of primordial gas, hundreds of thousands of times heavier than our Sun, collapsing directly under its own gravity. No star formation, no intermediate steps, just a sudden, catastrophic implosion into a black hole of staggering proportions. This direct collapse scenario would create a ready-made monster, skipping the slow growth phase entirely. But there's another possibility. Smaller black holes might have merged and gorged themselves at breakneck speed. In the chaotic early universe, dense clusters of stars and gas could have fed black holes so rapidly that they ballooned to supermassive proportions in just a few 100 million years. Some even speculate that extreme conditions might have allowed black holes to swallow entire stars in single, violent bites, accelerating their growth beyond anything we see today. The real enigma is that both theories have gaps. Direct collapse requires perfect, near-impossible conditions in the infant cosmos, while rapid growth demands a feeding frenzy unlike anything we've observed. Yet, somehow, these black holes exist lurking in the hearts of galaxies far older than they should be. So which is it? Did they emerge fully formed like cosmic gods, or did they feast their way to dominance in an era when the universe was still taking shape? The answer might rewrite the story of how everything, including us, came to be. Even if supermassive black holes formed early, there's another head-scratching problem. How did they grow so unimaginably massive so fast? We're talking about black holes weighing billions of times our sun's mass, existing when the universe was less than a tenth of its current age. It's like finding a skyscraper in the middle of a construction site that's only been active for a day. The math just doesn't add up. At the heart of this mystery lies what scientists call the seed problem. Normally, black holes grow by slowly pulling in gas, dust, and the occasional star, a process called accretion. But here's the catch: there's a speed limit to this cosmic buffet. It's called the Eddington limit. The maximum rate matter can fall into a black hole before the radiation it emits pushes everything else away. Think of it like trying to drink a milkshake through a straw. If you suck too hard, the pressure blows the straw right out of the cup. Under normal conditions, a black hole would take billions of years to reach supermassive status by nibbling at this restricted diet. Yet somehow the early universe cheated. That's where things get wild. Some astrophysicists argue these black holes didn't play by the rules. They gorged themselves in a frenzy called super-Eddington accretion. Picture a star venturing too close, getting shredded into a swirling disk of superheated plasma. Under extreme conditions, that disk could become so dense and chaotic that radiation can't escape fast enough to halt the feast. The black hole would binge, swallowing material hundreds or even thousands of times faster than normal. It's the cosmic equivalent of winning an all-you-can-eat lottery. But not everyone's convinced. Others propose an even stranger idea. What if the seeds weren't ordinary black holes at all? Enter primordial black holes, hypothetical monsters forged not from dying stars, but from the violent density fluctuations in the universe's first seconds. These ancient relics, if they exist, could have been born with masses thousands of times greater than typical stellar black holes, giving them a head start in the growth race. Some might even have survived to this day, drifting unseen through galaxies like invisible ghosts. Then there's the dark horse theory, black hole mergers. In the crowded cores of early galaxies, smaller black holes could have slammed together over and over, rapidly snowballing into giants. But this raises another question: how did they find each other so quickly in the vastness of space? The dance of gravity would need to be perfectly choreographed, with black holes spiraling inward without getting flung away. It's like trying to orchestrate a cosmic mosh pit where everyone collides at exactly the right moment. The truth might be a mix of all these ideas, or something we haven't even dreamed up yet. Every time we think we've cracked the code, the universe throws another curveball. Observations of distant quasars, simulations of the early cosmos, even the faint echoes of gravitational waves, all hint that the story of supermassive black holes is far stranger than we imagined. And until we solve it, their impossible growth remains one of the greatest cosmic riddles of all. At the center of our Milky Way, a sleeping giant rests Sagittarius A star, a supermassive black hole 4 million times heavier than our Sun. Unlike its brilliant, ravenous cousins powering distant quasars, it lies eerily quiet. This cosmic hibernation raises a chilling question: what makes a black hole with infinite appetite suddenly stop feeding? The answer might rewrite our understanding of galactic life cycles and reveal why Earth exists in such a peaceful corner of the universe. Active quasars shine with the brightness of a trillion stars, their supermassive black holes feasting on torrents of gas and stars. But Sagittarius A star barely whispers, its last major meal likely occurring when dinosaurs still roamed Earth. The difference comes down to galactic plumbing. Picture two kitchens, one overflowing with ingredients, the other nearly empty. Quasars sit in galaxies where chaotic collisions funnel vast amounts of material into the central black hole. Our Milky Way, by contrast, is orderly. Stars orbit in stable patterns, rarely straying close enough to be devoured. It's the cosmic equivalent of a well-organized pantry where snacks stay just out of reach. But there's a twist. Even in starved black holes like Sagittarius A star, astronomers catch occasional flickers, bursts of X-rays, or twisted jets of plasma flaring to life. These reveal a startling truth: dormant doesn't mean dead. Black holes might snack when passing gas clouds or stars veer too close, offering glimpses of their latent power. In 2019, Sagittarius A star suddenly brightened by 75 times for a few hours. Was it a rogue asteroid torn apart, a clump of interstellar gas slipping past the event horizon? Whatever it was, it proved these silent behemoths are always watching, always waiting. The real mystery lies in the switch what flips a galaxy from quasar frenzy to quiet slumber. Some blame galactic mergers. When two galaxies collide, their central black holes feast on the resulting chaos before eventually merging themselves. The recoil from this collision might kick the newborn black hole into a barren region of space, cutting off its food supply. Others point to feedback loops where the black hole's own energy blows away nearby gas like a cosmic leaf blower. Too much success leads to starvation, a self-regulating diet written into the laws of physics. Then there's the wild card, dark matter. Some theories suggest invisible halos of this elusive substance could stabilize galactic centers, preventing gas from falling inward. It's like an unseen hand gently holding back the cosmic buffet. Without it, even quiet black holes like ours might have grown into ravenous monsters, sterilizing their galaxies with lethal radiation long before life could emerge. The silence of Sagittarius A star might feel eerie, but it's a blessing. Its restraint allowed our galaxy to cool, stars to form, and planets like Earth to exist. Yet the same forces that lull it to sleep could one day stir it awake. If a gas cloud the size of a star drifts too close, or if the Milky Way collides with the Andromeda Galaxy in 4 billion years, our sleeping giant could roar back to life, a reminder that in the cosmos, peace is only ever temporary. Imagine two supermassive black holes, each weighing billions of suns, locked in a gravitational waltz so powerful it shakes the fabric of space-time itself. This isn't theoretical, it's happening right now in colliding galaxies across the universe. Yet despite knowing these cosmic duos must exist, we've barely glimpsed them. The mystery of binary supermassive black holes challenges everything we thought we knew about how galaxies evolve, and the clues might lie in the faintest whispers of the cosmos. When galaxies merge, their central black holes should eventually spiral together, creating a binary system. But here's the puzzle. While we've found plenty of galaxy mergers, confirmed pairs of supermassive black holes are shockingly rare. The most famous candidate, OJ 287, shows telltale flares every 12 years like clockwork, hinting at a second black hole tugging at its partner. Yet even this evidence is indirect. The reason? These cosmic dances play out over timescales longer than human civilization. Watching two black hours inch closer over millions of years is like trying to see the hour hand move on a clock. The real enigma is the final parsec problem. As black holes spiral inward, they shed energy by flinging stars away, a process called dynamical friction. But once they're about 3 light-years apart, theory says they should stall. At this distance, there aren't enough stars left to steal their momentum. They're trapped in a near-endless orbit, like two sumo wrestlers circling each other, too exhausted to collide. Yet somehow, black holes do merge. We've detected the gravitational waves from smaller black hole collisions. So what breaks the stalemate for supermassive behemoths? One possibility involves gas-vast reservoirs of it. In gas-rich mergers, swirling disks around each black hole could create drag, sapping their orbital energy like treacle. Another wild card, a third black hole. If another interloper crashes the party, its gravity might kick the pair close enough to cross the finish line. It's a cosmic game of billiards where one well-aimed shot solves everything. Then there's the detective work of gravitational waves. When binary black holes finally merge, they unleash ripples in spacetime so powerful they outshine every star in the universe combined for about 15 minutes. LIGO and Virgo have caught waves from stellar mass black holes, but supermassive binaries emit lower frequency waves needing space-based detectors like LISA, set to launch in the 2030s. Until then, we're listening to the universe with earplugs in, missing its loudest songs. The scarcity of observed pairs might also be an illusion. Some black holes in binaries could be hidden, like one dancer cloaked in shadow. If one black hole isn't actively feeding, it won't produce the telltale X-rays or jets we typically hunt for. Others might merge faster than expected, leaving only a single distorted event horizon as evidence. Or perhaps we're just impatient. The universe operates on its own timetable, and human telescopes have barely begun their watch. Every unanswered question about these binary giants forces us to rethink how galaxies grow. Their mergers may seed the universe's largest black holes, shape galactic structures, and even determine whether new stars can form. Each hidden pair we uncover will rewrite the story of cosmic evolution, one gravitational whisper at a time. Some of the most violent displays in the universe erupt not from black holes themselves, but from the colossal jets of energy screaming away from them at nearly the speed of light. These relativistic jets stretch for thousands of light years, punching through galaxies with enough force to reshape entire regions of space. Yet their existence poses a baffling question. How can something known for devouring everything nearby simultaneously blast matter outward with such unimaginable power? The answer lies in a cosmic tug-of-war between gravity and magnetism, where the rules of physics bend to their breaking point. At the heart of this mystery is the Blandford-Zenagic process, the leading theory for how black holes power their jets. Picture the black hole's event horizon as a cosmic battery spinning at dizzying speeds. As magnetic fields thread through this whirling abyss, they twist into coils tighter than any spring, storing staggering amounts of energy. When these fields snap like rubber bands stretched too far, they fling superheated plasma outward along the black hole's poles at velocities approaching light speed. It's nature's ultimate particle accelerator, turning a bottomless pit into a cosmic cannon. But not all black holes fire these jets, and that's where the debate ignites. Some researchers argue spin is the key. Only rapidly rotating black holes can wind magnetic fields tight enough to launch jets. Others point to the accretion disk's thickness. Thin, orderly disks might channel energy cleanly into jets, while turbulent, thick disks could choke them off like a clogged exhaust pipe. Then there's the wild card of magnetic field alignment. If the black holes spin and its disk's magnetic fields misalign, the resulting chaos might disrupt jet formation entirely. Alternative theories push the boundaries even further. The Penrose process suggests jets might steal energy directly from a black hole's rotation, like siphoning gasoline from a runaway car. In this scenario, particles near the event horizon could split, with one fragment falling in while the other rockets away, carrying stolen rotational energy. Meanwhile, the magnetically arrested disk model proposes that jets form when magnetic pressure becomes so strong it temporarily halts incoming matter, creating a standoff where energy has nowhere to go but up and out. The real enigma lies in the outliers. Why does M87's black hole, 6.5 billion solar masses, shoot a jet visible across the universe, while Sagittarius A star, our own galactic giant, remains eerily quiet? Observations reveal even black holes of similar size and spin behave differently, hinting at hidden variables we haven't yet grasped. Some jets flicker unpredictably, others pulse like clockwork, and a few even curve mysteriously mid-flight, as if guided by invisible hands. What's clear is that these jets aren't just cosmic fireworks, they're universe shapers. By heating surrounding gas, they can stifle star formation in entire galaxies or trigger it anew. Their radiation reaches us billions of years later as brilliant quasars, markers of black holes in their most ferocious youth. And if we could harness even a fraction of their energy, it would eclipse all human power consumption 1 trillion times over. Yet for all their fury, the secrets of their birth remain locked within the chaos of the event horizon, a reminder that even in destruction, black holes are creators. Between the stellar mass black holes born from collapsing stars and the supermassive giants lurking in galactic cores, there should be a missing link, black holes weighing thousands to hundreds of thousands of suns. These intermediate mass black holes could hold the key to solving one of cosmology's greatest puzzles. How did the first supermassive black holes grow so large so fast? Yet despite decades of searching, these cosmic middleweights remain frustratingly elusive, appearing only in fleeting glimpses that vanish upon closer inspection. Take HLX-1, the brightest candidate ever found. Nestled on the outskirts of a galaxy 300 million light-years away, this bizarre object flares with X-rays 10,000 times brighter than any known stellar black hole, yet far dimmer than a true supermassive one. For years, it seemed like the smoking gun, a black hole roughly 20,000 solar masses caught red-handed as it shredded a captured star. But when astronomers looked closer, HLX-1's light flickered unpredictably, leaving room for doubt. Could it be an unusually bright stellar black hole, a rare type of supernova imposter? The debate rages on, highlighting how even our best candidates slip through the cracks of classification. Part of the challenge is their stealthy nature. Unlike supermassive black holes that announce their presence with brilliant quasars, intermediate mass black holes have no signature feeding style. Too small to sustain constant accretion disks, yet too large to produce the telltale X-ray bursts of stellar black holes snacking on companion stars, they linger in cosmic shadows. Some might reveal themselves only during rare tidal disruption events, when a wandering star gets too close and is torn apart in a single spectacular meal. Others could hide in dense globular clusters, their gravity subtly distorting the orbits of surrounding stars like invisible hands stirring a celestial pot. The stakes couldn't be higher. If these middleweights exist in significant numbers, they'd bridge the gap between stellar remnants and galactic behemoths, offering a natural pathway for supermassive black hole growth. Picture them as cosmic stepping stones, small black holes merging in the early universe to form intermediates, which then collide or feed rapidly to become supermassive. Without them, the leap from a 50 solar mass black hole to one weighing billions of suns becomes a statistical nightmare, like expecting a pebble to grow into a mountain overnight through random dust accumulation. Yet alternative theories persist. Some suggest supermassive black holes skip the intermediate stage entirely, forming directly from collapsing primordial gas clouds. Others propose that extreme environments like the cores of dense star clusters allowed small black holes to merge and grow exponentially faster than we thought possible. The truth might lie in a cosmic conspiracy of silence. Intermediate black holes could be out there, but their quiet lifestyles make them nearly impossible to spot unless they're caught in the act of feeding. New hope comes from gravitational wave astronomy. As detectors like LIGO and Virgo become more sensitive, they might catch the mergers of these elusive objects, ripples in space-time carrying the unmistakable fingerprint of black holes weighing thousands of suns. Each chirp from the cosmic void could rewrite our understanding of black hole evolution, proving once and for all whether the missing link truly exists or if the universe played by different rules entirely. Until then, the hunt continues, a detective story written in X-ray flickers, distorted star orbits, and the patient unraveling of gravity's deepest secrets. There's a moment of cosmic horror when a star strays too close to a black hole's event horizon. Rather than being swallowed whole, it undergoes something far more violent, a tidal disruption event. Imagine the star stretching like taffy, its outer layers peeling away into a swirling disk of superheated plasma, while its core is shredded into a luminous stream of debris. This gruesome process unleashes a flare brighter than entire galaxies, a beacon signaling the black hole's hidden presence. Yet for all their fury, these events remain some of the universe's most perplexing phenomena, defying expectations at every turn. Take the case of Assassin 14 Lie. When astronomers spotted this flare in 2014, it checked all the boxes for a classic tidal disruption, a star torn apart by a black hole 20 million times the mass of our Sun. But then something strange happened. Instead of fading predictably, the flare rebrightened months later, as if the black hole had belched up a second course. Even stranger, it emitted X-rays in rhythmic pulses, like a cosmic lighthouse with a broken timer. Theories swirled. Perhaps the star's remnants formed a temporary accretion disk that wobbled unpredictably, or maybe the black hole's spin warped spacetime so severely that debris collided with itself in bizarre loops. Then there's the jet problem. Most tidal disruptions produce messy, omnidirectional flares as stellar debris rains down chaotically. But rare events like at 2019 DSG shoot focused relativistic jets, beams of plasma moving at nearly light speed. Why do some meals trigger jets while others don't? The answer might lie in magnetic field alignment. If the shredded star's material carries a strong, organized magnetic field into the accretion disk, it could funnel energy into tight columns along the black hole's poles, creating jets. Otherwise, the energy dissipates as a disorganized fireball. It's the difference between squeezing a water balloon versus capping a geyser. One splatters, the other streams violently. These events also serve as cosmic detectives, uncovering black holes we'd otherwise miss. In dwarf galaxies where supermassive black holes should be rare, flares like PS110J reveal monsters lurking where theory says they shouldn't exist. Others expose intermediate mass black holes, the elusive missing link between stellar and supermassive varieties, through the unique fingerprints of their flares. Smaller black holes shred stars quicker and hotter, while larger ones produce prolonged, cooler outbursts. Each disruption paints a portrait of the destroyer hidden within. Perhaps the greatest mystery is why some black holes hesitate. Models predict stars should be disrupted instantly, yet observations show flares that ramp up over weeks or even months. Could the star's own gravity briefly resist the black hole's pull, delaying the inevitable? Or does debris sometimes form a temporary barrier, like a logjam in a river, before catastrophically collapsing? Every outlier forces us to rewrite the textbooks, proving that even in death, stars have more to teach us about the darkest corners of the cosmos. Every massive galaxy seems to host a supermassive black hole at its core. But what's truly bizarre is how precisely the black hole's mass mirrors the galaxy's own properties. This cosmic balancing act called the M-sigma relation reveals an eerie symmetry. The heavier the black hole, the faster the stars in the galaxy's central bulge move. It's as if the invisible abyss somehow choreographs the dance of stars around it from behind the curtain. But here's the twist: no one knows whether the black hole sets the tempo, or if the galaxy itself dictates the size of its dark heart. The evidence is staggering. Measure the velocity dispersion of stars whipping around a galaxy's core, a statistic called sigma, and you can predict its central black hole's mass with uncanny accuracy. Take the Milky Way. Our stars orbit at about 100 kilometers per second near the center, and right on cue, Sagittarius A star weighs in at 4 million solar masses. Messier 87, with stars hurtling at 330 kilometers per second, hosts a black hole 6.5 billion times heavier than our Sun. This correlation holds across billions of light years, as if some hidden law of physics etched it into the fabric of the cosmos. So which came first, the galaxy or the black hole? One camp argues black holes play cosmic architect. Their violent outbursts, like quasars and jets, could blast away gas that would otherwise form stars, effectively putting a lid on galactic growth. Picture a toddler scribbling with crayons until an adult snatches them away. That might be how black holes regulate star formation, preventing galaxies from becoming too massive. Simulations show these feedback loops could explain the M-sigma relation, with black holes acting like invisible throttles on their host galaxies. But flip the script and another possibility emerges. Perhaps galaxies control their black holes' appetites. In denser environments, more gas funnels toward the center, feeding the black hole until it reaches equilibrium with its surroundings. It's like a tree's roots growing only as extensive as the soil allows, no more, no less. Some astronomers even suggest the relation emerges statistically over time, with mergers averaging out black hole masses to match their galactic homes. Then there are the rule breakers. NGC 1277's black hole is 10 times lighter than its galaxy's sigma predicts, while NGC 489's is suspiciously overweight. Some dwarf galaxies host surprisingly hefty black holes, while others lack them entirely. These outliers hint that the M-sigma relation isn't universal, just the dominant trend in a cosmos full of exceptions. The most tantalizing clue: ultra-compact dwarf galaxies. These tiny, dense star clusters shouldn't have supermassive black holes at all, yet some do, suggesting black holes might form first, seeding galaxies around them like dark scaffolding. Others think these dwarfs are stripped remnants of larger galaxies, their outer stars torn away while their black holes remained. Unraveling this chicken and egg dilemma isn't just academic, it's key to understanding how structure emerges in the universe. If black holes shape galaxies, then life itself might owe its existence to these invisible titans. Without their restraining influence, galaxies could burn through their gas too quickly, leaving no time for planets or us to form. Yet if galaxies dictate black hole growth, it implies an even deeper cosmic order, where gravity's dance writes the rules at every scale. The truth might lie somewhere in between, written in the silent dialogue between light and darkness that has shaped the universe since the beginning. Imagine standing near a tornado, feeling its winds rip everything apart, but on a cosmic scale, where the tornado is powered by a supermassive black hole, and its winds move at millions of miles per hour. These are accretion disk outflows, mysterious, high-speed gusts of matter and energy that blast outward from black holes with enough force to reshape entire galaxies. Yet despite their power, we still don't fully understand what launches them, or how they manage to influence star formation thousands of light years away. The sheer violence of these outflows defies logic. Gas swirling toward a black hole should be doomed, trapped by gravity's irreversible pull. But somehow, a fraction escapes, accelerated to speeds so extreme that it barrels through space like a cosmic hurricane. Some outflows are chaotic, spraying in all directions. Others form tightly collimated jets, and a few, like those in the quasar PDS 450, carry enough kinetic energy to outshine every star in their host galaxy combined. The mystery isn't just how they form, but why they're so selective. If black holes are insatiable eaters, why spit out precious fuel at all? One clue lies in magnetism. As gas spirals inward, magnetic fields threading through the accretion disk can twist into cosmic slingshots, flinging material outward before it crosses the event horizon. Think of it like a malfunctioning conveyor belt. Matter rides in, but turbulent forces keep hurling it back out. X-ray observations reveal these outflows are laced with iron and other heavy elements, proving they originate deep in the disk's heart, where temperatures soar to billions of degrees. Yet magnetism alone doesn't explain their reach. These winds don't just puff away weakly, they punch through interstellar space, crashing into surrounding gas clouds with enough force to compress or disperse them. This duality is key. In some galaxies, outflows act like cosmic snowplows, shoving gas away so violently that star formation grinds to a halt. No gas, no new stars. But paradoxically, in other cases, the same winds trigger collapses in distant clouds, seeding new stellar nurseries. It's as if a tornado could both demolish one town and fertilize fields in another. The biggest enigma is their unpredictability. Why do some black holes produce feeble puffs while others unleash galaxy-wide tempests? Observations of ultra-luminous infrared galaxies show outflows so powerful they're literally blowing their own galactic disks apart. Meanwhile, quiet black holes like Sagittarius A barely muster a breeze. Spin rate, disk thickness, and even the black holes feeding history might determine the ferocity of these phantom winds, but no single model explains all the variations we see. Then there's the dark matter wild card. Some theorists suggest invisible halos could focus or disrupt outflows, adding another layer of chaos to an already bewildering process. Others propose that the universe's largest outflows might be tapping into energy sources we haven't yet imagined, perhaps even relics from the black hole's formation. What's certain is that these phantom outflows are more than just black hole byproducts. They're cosmic regulators governing how galaxies live and die. Without them, galaxies might burn through their gas too quickly, leaving no time for stars or planets like ours to form. Yet with them, the universe maintains a fragile balance between chaos and creation, written in the language of wind and fire. A supermassive black hole isn't just a cosmic vacuum, it's a whirling dynamo spinning at speeds that defy comprehension. Some rotate so fast they nearly tear space-time itself apart, while others barely move at all. This isn't random chaos. A black hole's spin holds secrets about its birth, its violent past, and even its power to shape galaxies. But how do these colossal voids acquire their spin in the first place? And why do measurements reveal such wild extremes, from lethargic crawls to near light-speed frenzy? The answer begins with a black hole's diet. Just as a figure skater spins faster by pulling their arms in, a black hole accelerates when it feeds on material with aligned angular momentum. Imagine gas swirling around it like water circling a drain. If the flow is orderly, the black hole gulps it down and spins up. But here's the catch: not all meals are so tidy. Collisions with other black holes can deliver chaotic kicks, sometimes speeding up the spin, other times slamming the brakes. It's like trying to spin a merry-go-round while bystanders randomly grab hold or shove it in reverse. X-ray reverberation mapping has revealed just how bizarre these spins can be. By studying flickering X-rays from accretion disks, astronomers can peer close to the event horizon, where space-time itself is dragged into a whirlpool. Some black holes, like the one in galaxy MCG-63015, spin at almost 90% the maximum possible rate, a limit set by Einstein's equations. Others, like the behemoth in NGC 3007-8, barely rotate at all. The spread is so vast it suggests wildly different life stories. Fast spinners might have gorged on steady, aligned gas streams for eons, while slow pines could be the product of violent mergers that left them disoriented and sluggish. Then there's the jet connection. Spinning black holes are cosmic power plants, their rotation energizing magnetic fields that launch relativistic jets. The faster the spin, the tighter those magnetic coils wind, like a spring loaded to the breaking point. This might explain why some black holes, like M87s, fire jets hundreds of thousands of light years long, while others remain eerily quiet. But exceptions abound. A few sluggish black holes still manage to produce jets, hinting at hidden factors like misaligned disks or chaotic magnetic fields that defy the tidy spin jet paradigm. The real enigma is how spin shapes cosmic evolution. Rapidly rotating black holes might heat surrounding gas so efficiently they stifle star formation, creating red and dead galaxies. Others could act as gravitational catapults, flinging stars into chaotic orbits. And if black holes spin fast enough, they might even open portals to hypothetical realms, wormholes, though that remains firmly in the realm of speculation. What's clear is that spin isn't just a curiosity, it's a fingerprint of a black hole's violent history. Each rotation holds clues to the mergers it survived, the galaxies it consumed, and the cosmic winds it weathered. And as we measure more of these spins, we're finding they're as unique as the black holes themselves. No two whirl the same way in the dark. At the precipice of a black hole's event horizon, physics textbooks tell us there should be an invisible boundary, the last stable orbit. This is the point where gravity's grip becomes so overpowering that matter can no longer circle safely. Instead, it plunges inward, lost forever to the void. Yet recent observations have shattered this expectation, revealing material dancing closer to the abyss than Einstein's equations should allow. It's as if these cosmic monsters have torn up the rulebook, leaving astronomers scrambling to understand how the impossible is happening right before our eyes. The Gravity Telescope, perched atop Chile's high deserts, has been pivotal in this mystery. By combining the power of 4 giant telescopes, it acts like a cosmic magnifying glass, peering deeper into the chaotic swirl around black holes than ever before. In 2018, it spotted something bizarre around Sagittarius A star, clumps of superheated gas orbiting just outside the event horizon at nearly 30% the speed of light. According to general relativity, this material should have already crossed the point of no return. Instead, it whips around like a car skidding on the edge of a cliff, defying every prediction about where the last stable orbit should lie. One explanation: black hole spin warps spacetime so severely that it drags the last stable orbit inward, like a whirlpool pulling a boat closer before it sinks. A rapidly rotating black hole doesn't just bend space, it twists it into a vortex, altering the trajectories of nearby matter. Think of it as cosmic cheating. By spinning fast enough, the black hole redefines the boundaries of its own gravitational prison. But even this can't fully explain the gravity observations. Some material appears to linger in orbits that should be suicide, held aloft by forces we're only beginning to understand. Then there's the magnetic field wild card. Simulations suggest that powerful magnetic fields could act as invisible scaffolding, propping up gas that would otherwise fall. Picture a daredevil riding a motorcycle inside a spinning drum. The walls keep them from crashing downward. Similarly, magnetic turbulence might create enough outward pressure to counteract gravity's fatal pull, at least temporarily. This could explain why some black holes seem to have multiple last stable orbits, stacked like layers in an onion, each defying expectations in its own way. The stakes are higher than a physics puzzle. If matter can orbit closer than thought, it changes how we calculate black hole masses, spins, and even their growth rates across cosmic history. It might also solve the mystery of why some black holes flare unpredictably. Perhaps clumps of gas hover near the edge for months before finally slipping over, creating delayed bursts of light. The universe has a habit of revealing gaps in our knowledge precisely where we thought we had answers. And as telescopes grow sharper, these invisible walls, or lack thereof, may rewrite the laws governing the most extreme environments in existence. The most elusive substance in the universe might be hiding in plain sight, clustered around supermassive black holes like shadows around a flame. Dark matter, that mysterious invisible stuff making up 85% of the cosmos's mass, could be intimately tied to these gravitational monsters in ways we're only beginning to grasp. Some theories suggest black holes devour dark matter, growing fat on its unseen calories. Others propose dark matter acts like an invisible cage, shaping how black holes feed and spin. But the truth, it's stranger than anything we've imagined. Take the spike hypothesis. Dark matter should, in theory, pile up near black holes due to their insane gravity, forming dense halos that could reach millions of times the density of normal space. Yet we've never directly detected these spikes. Why? One possibility is annihilation. If dark matter particles collide and destroy each other in these crowded regions, they might unleash gamma rays, energy signatures we could spot. Fermi Gamma Ray Space Telescope has scanned black holes like Sagittarius A star for such signals, but the results are inconclusive. Some blips in the data hint at dark matter interactions, while others fade into background noise. It's like listening for whispers in a hurricane. Then there's the feeding question. Could dark matter actually nourish black holes? Most models assume black holes grow by eating gas and stars, but dark matter, if it interacts even weakly, might supplement their diet. Simulations show that certain types of dark matter, like WIMP, could get trapped in orbit around black holes, slowly spiraling inward over eons. The catch: dark matter doesn't behave like normal matter. It doesn't collide or compress into glowing accretion disks. Instead, it might flow into black holes like a ghostly river, invisible to our telescopes but subtly influencing their growth. But the plot thickens. Some galaxies host black holes far more massive than their stars suggest possible, as if something extra is feeding them. Could dark matter explain these outliers? In dwarf galaxies, where visible material is scarce, black holes sometimes outweigh expectations by a factor of 10. If dark matter halos in these small galaxies are unusually dense, their gravitational pull might funnel more dark matter, and thus more mass, into the central black hole. It's a cosmic loophole, a way for black holes to grow even when gas and stars are in short supply. The most radical idea: dark matter might not just surround black holes, it could alter their very nature. Certain theories suggest that under extreme gravity, dark matter particles could transform into something else entirely, perhaps even seeding primordial black holes in the early universe. Others speculate that dark matter's gravity could stabilize accretion disks, preventing them from collapsing too quickly and explaining why some black holes flare unpredictably. What's clear is that dark matter and black holes are locked in a cryptic dance, each shaping the other in ways we're desperate to decode. Every observation, from gamma-ray anomalies to gravitational wave signals, could be hiding clues. Until we solve it, the universe's darkest secret remains just out of reach, whispering from the event horizon's edge. Deep inside a black hole's event horizon, the universe faces an impossible choice: either destroy information forever, violating quantum mechanics, or set space itself on fire. This is the black hole information paradox, and when applied to supermassive black holes, it twists into something even stranger. At the heart of the conflict lies a simple question: what happens to all the quantum information? The unique properties of every atom, every particle, that falls into these cosmic voids. According to quantum theory, information can never be truly lost, yet black holes, by their very nature, seem to erase it completely. The contradiction is so severe that resolving it might require rewriting the laws of physics. Enter Hawking radiation. In the 1970s, Stephen Hawking realized black holes aren't completely black. Due to quantum fluctuations near the event horizon, they should slowly emit particles, a faint glow now called Hawking radiation. Over eons, this process causes black holes to lose mass and eventually evaporate. But here's the catch: Hawking radiation appears random, carrying no trace of the information that fell in. When the black hole vanishes, all that data vanishes with it. Quantum mechanics insists this can't happen, leaving us with an unsolvable riddle. For stellar mass black holes, this is troubling enough. But supermassive black holes crank the paradox to extremes. Take one like Ton 618, weighing 66 billion suns. Its Hawking radiation would be so weak that its evaporation would take longer than the current age of the universe. Yet even these behemoths aren't permanent. Given infinite time, they too would fade away along with every scrap of information they ever consumed. The scale is staggering. Trillions of stars, planets, and civilizations worth of quantum data snuffed out without a trace. That's where the firewall theory crashes in. One radical solution proposes that the event horizon isn't a smooth gateway but a searing wall of high-energy particles. Anything crossing it wouldn't gradually stretch, it would instantly vaporize. This firewall would preserve information by encoding it into the Hawking radiation, but at a horrific cost. General relativity's prediction of an uneventful horizon would be wrong. It's like discovering the edge of a waterfall isn't calm air but a curtain of flames. The stakes couldn't be higher. If firewalls are real, Einstein's theory of gravity fails at event horizons. If they're not, quantum mechanics might need an overhaul. Supermassive black holes complicate things further. Their immense gravity dilutes time near the horizon, meaning outside observers might never see anything cross it, while an infalling astronaut would hit the firewall in seconds. Two contradictory realities, both true depending on perspective. Alternative theories abound. Some suggest black holes don't evaporate completely but leave behind microscopic remnants, information-laden fossils. Others propose holographic principles where all 3D information is encoded on a 2D surface at the horizon. But each solution feels like rearranging deck chairs on the Titanic, patching one problem while creating others. What's clear is that supermassive black holes aren't just swallowing matter, they're exposing cracks in reality's foundation. And until we solve their paradox, we can't claim to understand how the universe truly works. What if the unfathomable depths of a supermassive black hole didn't lead to oblivion but to somewhere else? The wormhole hypothesis suggests these cosmic giants might not be endpoints at all but gateways. Einstein's equations actually permit such shortcuts through spacetime called Einstein-Rosen bridges. The math shows that if you distort gravity enough, like with a spinning black hole, a tunnel could form, connecting distant parts of the universe or even different universes entirely. But before you pack your bags for an interstellar road trip, there's a catch. Traditional wormholes would collapse instantly, crushed by their own gravitational forces before anything could pass through. Recent supercomputer simulations, though, have thrown this assumption into question. By modeling spinning black holes with plasma-filled accretion disks, physicists found that extreme rotational forces could theoretically keep a wormhole's throat open, at least temporarily. The key is frame dragging, where a rapidly spinning black hole twists spacetime around it like a whirlpool. This could counteract the collapse long enough for matter to traverse the tunnel. Some models even suggest that the wormhole's exit might resemble a white hole, a hypothetical region where energy and matter erupt outward but nothing can enter. Imagine diving into M87's black hole only to be spewed out somewhere in the Virgo cluster, millions of light years away, yet the hurdles are astronomical. For one, keeping a wormhole stable would require exotic matter with negative energy, something we've never observed. Quantum fluctuations near the event horizon might provide this, but the amounts needed would dwarf anything found in nature. Then there's the tidal forces. Even if a wormhole stayed open, the gravitational gradients would likely shred any object or signal trying to pass through. It's like imagining a tunnel through a mountain where the walls are made of spinning knives. The most tantalizing clues come from black hole mergers. When LIGO detected gravitational waves from colliding black holes, some physicists scrutinized the signals for anomalies echoes that might suggest the presence of a wormhole throat rather than a singular event horizon. So far, no such echoes have been confirmed, but the search continues. Other researchers are studying quasars, looking for odd light patterns that could hint at wormhole lensing effects. Perhaps the most sobering reality check comes from entropy. Black holes are the universe's ultimate trash compactors, and wormholes would need to preserve that function while somehow also allowing information transit. The laws of thermodynamics might slam the door shut on this idea before physics even gets a chance. But in a cosmos where dark energy accelerates expansion and quantum particles teleport, ruling anything out completely would be short-sighted. For now, wormholes remain in the realm of fascinating speculation, a reminder that even the universe's most destructive forces might hide portals to the unimaginable. At the boundary of a supermassive black hole's event horizon, the universe might be performing an impossible magic trick, flattening three-dimensional reality into a two-dimensional code. This mind-bending idea, known as the holographic principle, suggests that everything we perceive, stars, galaxies, even our own bodies, could be nothing more than a cosmic projection, like a movie played across the surface of a black hole's shadow. The mathematics behind this theory is so profound that it could rewrite our understanding of space, time, and information itself. The roots of this idea trace back to the black hole information paradox. When matter falls into a black hole, its quantum information, the unique properties defining every particle, seems to vanish. But quantum mechanics insists information can't be destroyed. The holographic principle offers a solution. The information isn't lost. Instead, it's smeared across the event horizon like ink on a bubble, preserved in a scrambled two-dimensional form. Imagine taking a novel and burning it. The words seem gone, but if every fleck of ash retained a fragment of the text, the story could still be reconstructed. That's what spacetime might be doing at the edge of a black hole. The AD/CFT correspondence, a groundbreaking concept from string theory, takes this further. It proposes a literal duality, a dictionary translating events inside a warped, higher dimensional space like a black hole's interior into a lower dimensional theory on its boundary. Picture a room where every object, every shadow, is perfectly mirrored by patterns painted on the walls. The three-dimensional room is the black hole's interior. The two-dimensional paint is the event horizon's encoded data. This isn't just philosophy, it's hard math with equations showing how gravity in 5 dimensions could be mathematically equivalent to quantum physics in 4. Supermassive black holes turn this from abstraction into a cosmic laboratory. Their vast event horizons provide the ultimate canvas for holographic encoding. A black hole like TUN 618, with a horizon larger than our solar system, could store information at a density of 1 bit per Planck area, the smallest possible unit of space. That means every square automata, a billionth of a centimeter, might hold a fragment of the universe's deepest secrets, yet mysteries remain. If the universe is a hologram, why do we perceive it in 3 dimensions? Some theorists suggest our reality is a projection from a distant, two-dimensional surface at the edge of the cosmos. Others argue that black holes are localized holograms, with their event horizons acting as private servers storing fallen data, the most radical idea. Every black hole's surface might be stitching together patches of a grand cosmic code, like pixels assembling an image we can't yet see. The implications are staggering. If true, the holographic principle means that space itself is an illusion, a convenient interface for something far stranger. It could unify quantum mechanics and gravity, solving physics' greatest dilemma. And supermassive black holes, with their monstrous horizons and gravitational might be the universe's ultimate hard drives, silently preserving every scrap of reality in a language we're only beginning to decipher. The frontier of a black hole isn't just a point of no return. It could be the screen on which existence is projected. Right outside a spinning supermassive black hole, time doesn't just slow, it twists into knots. This phenomenon, called frame dragging, turns the fabric of spacetime into a swirling vortex where the rules of clocks and calendars unravel completely. Picture a spoon stirring honey. The spoon represents the black hole's spin, and the honey is spacetime itself, dragged along in its rotation. The faster the spin, the more extreme the distortion, warping reality so severely that an astronaut orbiting close enough could watch entire civilizations rise and fall in what feels like mere hours. We've seen this effect on small scales around Earth. Gravity Probe B, a NASA satellite, detected frame dragging in our planet's weak gravity field, a minuscule shift of just a few thousandths of a degree per year. But near a rapidly spinning black hole like GRS 1915+105, the effect becomes apocalyptic. Simulations show its spin drags spacetime around it at nearly light speed, creating a whirlpool so intense that falling into orbit would feel like being caught in a cosmic riptide. Even light struggles to resist, its path bent into spirals as space itself rotates beneath it. This is where time dilation reaches its breaking point. Remember the ocean planet from Interstellar, where 1 hour equaled 7 years back on the ship? That's not Hollywood exaggeration, it's grounded in real physics. Near a spinning black hole's ergosphere, the region outside the event horizon where frame dragging becomes inescapable, time stretches to unimaginable extremes. A single orbit could span millennia elsewhere in the universe. Imagine 2 astronauts, one orbits the black hole while the other stays far away. When they reunite, the orbiting astronaut might have aged days, while their partner could be centuries older, if not dust. The most mind-bending consequence, causality starts to fray. At certain spin thresholds, mathematical models suggest closed time-like curves could form loops where an object's future bends back into its own past. It's the ultimate time warp, a path where cause and effect circle endlessly like a snake eating its tail. Of course, nature likely prevents such paradoxes through quantum effects or hidden physics. But the mere possibility hints at how black holes don't just bend space, they rewrite the very syntax of time. Yet for all their power, these time-twisting monsters leave clues. Astronomers study flickering X-ray signals from orbiting gas clouds, watching as frame dragging delays some light pulses and accelerates others. Each flicker is like a timestamp, revealing how spacetime churns near the event horizon. Future missions, like the European Space Agency's LISA gravitational wave detector, could map these distortions in unprecedented detail, turning theoretical curiosities into measurable facts. What remains terrifying and thrilling is that these aren't thought experiments. Somewhere in the cosmos right now, a supermassive black hole spin is stretching seconds into eons, proving that time was never the constant we believed. It's fluid, malleable, and in the right conditions, as fragile as a thread pulled taut over an abyss. One of the most baffling discoveries in modern cosmology is that the universe isn't just expanding, it's accelerating. Scientists call the mysterious force behind this phenomenon dark energy, and it makes up nearly 70% of the cosmos, yet its origin remains completely unknown. Now, a radical new hypothesis suggests an unlikely culprit: supermassive black holes. Could these gravitational behemoths, long thought to be cosmic destroyers, actually be fueling the universe's runaway expansion? The theory hinges on a startling observation from 2023. Astronomers studying elliptical galaxies found something bizarre. The mass of their central black holes appeared to grow over time, even when no nearby matter was available for them to consume. The numbers were off by orders of magnitude. Take Galaxy M87, home to a black hole weighing 6.5 billion suns. Standard models predicted it should grow by a fraction of a percent over billions of years. Instead, its mass seemed to balloon in ways that defied conventional physics. The key clue: the expansion rate matched the universe's acceleration, almost as if the black holes were somehow tied to dark energy itself. This led to the vacuum energy hypothesis. Supermassive black holes might contain cores of pure vacuum energy, the same force driving cosmic acceleration. As they grow, their event horizons expand, increasing the volume of this exotic energy trapped inside. The result: a feedback loop where black holes don't just live in the universe, they actively reshape it. Think of them as cosmic batteries. The more they store, the more they push space apart, but not everyone's convinced. Critics argue this could be an observational fluke. Black hole masses are notoriously hard to measure. Others suggest alternative explanations like dark matter interactions or hidden accretion flows. Yet the correlation is tantalizing. If confirmed, it would mean black holes aren't mere passengers in an expanding universe. They might be its architects. The implications are staggering. It would mean that the very objects tearing stars apart are also stitching the cosmos together, threading dark energy into the fabric of spacetime itself. And if true, it could solve one of physics' greatest mysteries, why the universe's expansion started accelerating 5 billion years ago. Perhaps that's when supermassive black holes reached a critical threshold, their combined vacuum energy tipping the cosmic scales. Future tests could settle the debate. Gravitational wave detectors might catch mergers where black holes behave unexpectedly, their masses warping space in ways that hint at hidden energy. Telescopes like the Vera Rubin Observatory could track growth rates across millions of galaxies, searching for patterns that link black holes to cosmic acceleration. For now, the idea remains controversial, but that's the beauty of science. The universe's darkest secrets often hide in plain sight, waiting for someone to ask the right question. And if supermassive black holes are indeed the source of dark energy, it would rewrite not just our understanding of them, but of reality itself. Some of the most bizarre theories about supermassive black holes don't come from astrophysics journals. They emerge from the blurry line between science and science fiction. One persistent myth suggests these cosmic giants aren't natural phenomena at all, but power plants for advanced alien civilizations. The idea goes like this: what if a hyper-intelligent species could wrap a quasar in a Dyson sphere, a megastructure harvesting its unimaginable energy? It's a tantalizing thought experiment until you hold it up to the harsh light of reality. The concept borrows from real astronomy. Dyson spheres, first proposed by physicist Freeman Dyson in the 1960s, are hypothetical shells built around stars to capture their full energy output. Scale that up to a quasar, a supermassive black hole devouring matter so furiously it outshines galaxies, and you've got an engine capable of powering a civilization billions of years more advanced than ours. Some theorists even point to oddities in quasar light curves, unexplained dimming or spectral anomalies as potential technosignatures of such structures. But here's where Occam's razor slices through the speculation. Quasars already have a perfectly natural explanation: accretion disks of superheated gas, twisted magnetic fields, and relativistic jets. No exotic technology is required to explain their brilliance. Those strange light patterns, they're more likely caused by intervening dust clouds, microlensing effects, or the chaotic dynamics of the disks themselves. The universe is messy enough without inventing cosmic engineers. That said, the myth persists for good reason. Supermassive black holes are the universe's ultimate batteries, converting matter into energy with terrifying efficiency. If any civilization could harness them, they'd unlock power beyond comprehension. A single quasar emits enough energy in 1 second to meet Earth's needs for 1 trillion years. The temptation to imagine such mastery is irresistible, like ancient humans gazing at lightning and dreaming of taming it. Perhaps the most intriguing twist is that the idea isn't entirely impossible, just implausible with our current knowledge. The Kardashev scale, which ranks civilizations by energy use, places Type 3 civilizations at the top, those controlling the output of entire galaxies. Could such beings exist? Maybe. But if they do, they're likely playing with forces even weirder than black holes, dark energy, quantum vacuums, or dimensions we can't perceive. In the end, the alien megastructure myth says more about us than about quasars. It reveals our hunger to find purpose in the cosmos, to believe that even the most violent phenomena might serve some higher order. But the truth is stranger still. Nature doesn't need aliens to build wonders. Supermassive black holes, left to their own devices, are already the most dazzling engines in existence, no engineers required. Stretching across the observable universe like a vast neural network, the cosmic web connects galaxies through shimmering filaments of gas and dark matter. But at the intersections of these colossal threads, where multiple strands converge, something extraordinary lurks. Nearly every node in this cosmic net hosts a supermassive black hole, as if these gravitational behemoths were placed there deliberately to anchor the structure of reality itself. Their presence isn't random coincidence, it's evidence of a hidden symbiosis between the universe's largest structures and its darkest inhabitants. Consider the spiderweb galaxy, a chaotic knot in the cosmic web where 12 galaxies collide. At its heart lies a supermassive black hole surrounded by the largest reservoir of molecular gas ever observed, enough raw material to birth millions of stars. This isn't an anomaly, it's the rule. Simulations show how black holes act like cosmic vacuum cleaners, sucking in intergalactic gas along filaments of the web. But instead of simply swallowing it, they redirect this primordial fuel. Some gas falls beyond the event horizon, but much gets superheated and blasted outward in high-speed jets, seeding new generations of stars across entire galaxy clusters. It's a feedback loop on a cosmic scale. Black holes shape the web that feeds them, which in turn shapes the destiny of galaxies. The mathematics behind this process is staggering. When two filaments intersect, gravity causes gas to pile up at the node, a gravitational well deep enough to trap matter for eons. Supermassive black holes amplify this effect, their immense pull creating a funnel that directs gas flows across millions of light years. Picture a whirlpool at the confluence of two rivers, but one where the swirling currents sculpt the landscape for galaxies yet to form. Some astronomers compare these nodes to metabolic centers in a living organism, processing raw materials and redistributing energy to keep the cosmic system alive. Yet mysteries remain. Why do some nodes host multiple black holes locked in orbital dances while others have just one dominant monster? Observations of the Coma cluster reveal black hole binaries at web nodes, suggesting mergers play a critical role in shaping these intersections. Then there's the puzzle of dark nodes, regions where the cosmic web's geometry predicts a supermassive black hole, yet telescopes find nothing. Are these voids hiding dormant giants, or does the web itself occasionally spawn new black holes from collapsing dark matter? The implications rewrite our understanding of cosmic evolution. Without black holes anchoring these junctions, the cosmic web might lack the stability to form galaxy clusters. Their gravity not only draws in matter but also generates shock waves that prevent gas from cooling too quickly, a delicate balance allowing stars to form at sustainable rates. In this light, supermassive black holes aren't just occupants of the cosmic web. They're its architects' invisible hands weaving the grandest structure in existence. For every supermassive black hole blazing at a galaxy's heart, there could be dozens of cosmic phantoms drifting silently through the darkness, black holes that left no trace behind. These invisible exiles might lurk between galaxies, hide in the sparse outskirts of galaxy clusters, or even float alone in the voids where almost nothing else exists. They're the ultimate cosmic ghosts, massive enough to warp space, yet so isolated that not even starlight betrays their presence. Current telescopes can't find them, but their gravitational whispers hint at a hidden population that could redefine what we know about black holes' origins and fates. Take the case of wandering supermassive black holes. When galaxies collide, their central black holes spiral inward, but sometimes, especially in unequal mergers, the smaller black hole gets slingshot into the void. Simulations show up to 10% of supermassive black holes could be ejected this way, left to wander intergalactic space like ships without harbors. Some might still carry remnants of their old accretion disks, faintly glowing for millions of years before fading entirely. Others could drift unseen, detectable only if they passed directly between us and a distant star, bending its light in a fleeting moment of gravitational lensing. Then there are the primordial relics, black holes that formed not from dying stars, but from the raw density fluctuations of the early universe. These could range from asteroid size to thousands of solar masses, peppering galaxy halos or floating in cosmic voids. The most tantalizing candidates are the overmassive black holes found in tiny, gas-poor galaxies. Their weights far exceed what standard formation models predict, suggesting they might be ancient stragglers from a time before galaxies even existed. The hunt for these phantoms is pushing astronomy to its limits. Projects like the upcoming Nancy Grace Roman Space Telescope will scan for microlensing events, subtle flickers caused by invisible black holes warping background starlight. Others search for rogue black holes by tracking hypervelocity stars flung away at insane speeds during close encounters. Some might even betray themselves by plowing through gas clouds, creating shock waves visible in radio telescopes. But the most promising clues could come from gravitational waves. Future observatories like LISA might catch the mergers of these nomads, their space-time ripples carrying echoes of collisions that happened far from any galaxy. Each detection would rewrite the cosmic ledger, proving that black holes don't just rule galaxies, they haunt the emptiness between them. Until then, their shadows linger at the edge of our vision, a reminder that the universe always keeps its darkest secrets just out of reach. A supermassive black hole's event horizon might seem like the ultimate edge of darkness, but just beyond it lies a hidden storm of magnetic fury. These invisible force fields, trillions of times stronger than Earth's, don't just surround black holes, they control them. Like puppet masters, they shape jets, twist accretion disks, and even dictate how fast a black hole can feast. The Event Horizon Telescope's groundbreaking polarized light images of M87's black hole revealed this magnetic chaos in stunning detail, showing field lines arcing through superheated plasma like cosmic spiderwebs. Yet for all we've seen, the origins of these magnetic monsters remain one of astrophysics' most perplexing riddles. Take the jet launching mechanism. While gravity pulls matter inward, magnetic fields act as cosmic catapults, flinging particles outward at nearly light speed. Simulations show that as gas spirals into the accretion disk, it drags embedded magnetic fields along like threads caught in a whirlpool. These fields grow tighter and more twisted until, like a rubber band stretched too far, they snap, releasing enough energy to power jets that stretch for thousands of light years. But here's the puzzle. Some black holes produce perfectly collimated jets, while others spew chaotic outflows, the difference likely the magnetic field's alignment. Ordered fields create focused jets, tangled ones produce disordered winds. The real shock came when the Event Horizon Telescope captured polarized light around M87's black hole, light that had traveled through these magnetic maelstroms. The images revealed a striking spiral pattern, suggesting fields strong enough to resist being swallowed whole. Instead of disappearing into the abyss, these magnetic loops appear to circle the event horizon like a cage, possibly even slowing down the black hole's spin over eons. It's as if the void itself is fighting back against its own hunger. Yet the biggest mystery isn't what these fields do, it's where they come from. One theory suggests they're fossil relics left over from the magnetic chaos of the galaxy's formation. Another proposes they're self-generated, amplified by the churning motions of the accretion disk like a dynamo. Then there's the dark horse idea. Quantum effects near the event horizon could spontaneously create magnetic fields from the vacuum itself, birthing forces where none existed before. What's clear is that without these magnetic monsters, black holes would be far less powerful and the universe far less interesting. They're the invisible hands shaping some of the cosmos' most violent spectacles, proving that even in the darkest voids, magnetism writes the rules. And as telescopes peer deeper, each new image peels back another layer of this magnetic mystery, revealing just how much we still don't understand about the forces that govern the abyss. The universe holds onto its earliest moments like a fading echo ripples in space-time from the Big Bang itself, still resonating across nearly 14 billion years. These primordial gravitational waves carry whispers of creation, a background hum from when reality was smaller than an atom, and hidden in this cosmic static might be the fingerprints of supermassive black holes, not as they exist today, but as they first formed in the universe's violent infancy. The key to unlocking this mystery listening for their collisions with instruments so precise they could detect a star's wobble from across the galaxy. Future observatories like LISA, the Laser Interferometer Space Antenna, aim to catch these echoes. Unlike ground-based detectors such as LIGO, which pick up high-frequency waves from stellar mass black holes, LISA trio of satellites will float 2.5 million kilometers apart, sensing low-frequency ripples that could reveal supermassive black hole mergers from the dawn of time. The math is staggering. When two of these titans collide, they warp spacetime so profoundly that the resulting waves might still be traveling today, subtly stretching and squeezing the fabric of the cosmos. It's like dropping a boulder into a pond and waiting for the ripples to return, except the pond is the universe, and the boulders are black holes weighing billions of suns. But here's the twist. The loudest signals might not come from black holes merging in the present era, but from their ancestors, primordial black holes forged in the first chaotic seconds after the Big Bang. Some theories suggest these ancient monsters could have served as seeds for today's supermassive giants, growing by gorging on gas or merging with others in the cosmic dark. If LISA detects gravitational waves with specific frequencies or patterns, it could confirm whether supermassive black holes have roots stretching back to the universe's birth. The implications would rewrite cosmology. If primordial waves bear the signature of supermassive black holes, it would mean these objects aren't just byproducts of galaxy formation. They're relics from a time before stars, before atoms, even before light could travel freely. Their mergers would act as time capsules, preserving information about conditions so extreme that no other trace remains. Some models even suggest these waves could reveal hidden dimensions or cracks in Einstein's theory of gravity, offering clues to physics beyond our current understanding. Yet the hunt is fraught with challenges. Primordial waves are buried under the cacophony of later cosmic events, black hole mergers, neutron-star collisions, even the orbital motion of distant stars. Teasing out the faintest signals requires algorithms sharp enough to isolate a whisper in a hurricane. And if the waves are too weak, they might slip past our detectors entirely, leaving the universe's earliest secrets forever out of reach. That's what makes this search so thrilling. It's not just about black holes, it's about decoding the universe's origin story from the vibrations they leave behind. Every merger, every ripple is a note in a symphony that began with the Big Bang. And with LISA launch in the 2030s, we might finally tune in to the echoes of creation itself. What if humanity's ultimate energy source isn't on Earth, or even in our solar system, but orbiting the event horizon of a supermassive black hole? The Penrose process, a daring idea from physicist Roger Penrose, suggests these cosmic monsters could be harnessed like galactic power plants. By tapping into the rotational energy of a spinning black hole, a civilization could theoretically extract enough power to sustain itself for eons, far surpassing anything achievable with stars, fusion, or antimatter. The numbers are staggering. A single supermassive black hole like M87 could provide energy equivalent to annihilating thousands of suns every second, all without burning a single drop of fuel. Here's how it would work. A spinning black hole drags spacetime around it, creating a region just outside the event horizon called the ergosphere, where nothing can stand still. If you were to fire a projectile into this zone, it could split into two fragments through quantum effects. One fragment falls into the abyss, but the other could emerge with more energy than it entered with, having stolen a fraction of the black hole's spin. This isn't perpetual motion, it's gravity's ultimate sleight of hand. Over time, repeated extraction could slow the black hole's rotation, converting its angular momentum into usable energy on an astronomical scale. The implications for a Kardashev Type 3 civilization, one capable of harnessing the energy output of an entire galaxy, are mind-bending. Imagine a Dyson swarm not around a star, but around a black hole's accretion disk, capturing X-rays and gamma rays emitted by infalling matter. Pair that with Penrose extraction, and you've got an energy surplus dwarfing anything in nature. Calculations suggest a supermassive black hole could power quadrillions of advanced societies simultaneously, enough to run planet-sized supercomputers, warp drives, or even megastructures we can't yet conceive. But the challenges are as monumental as the rewards. Engineering a Penrose reactor would require structures capable of withstanding tidal forces that shred atoms, not to mention relativistic speeds and temperatures exceeding millions of degrees. Even positioning the energy collectors would demand precision beyond anything humans have achieved, like threading a needle from light years away. And there's a catch: overusing the process could eventually break the black hole's rotation, turning it from an energetic dynamo into a sluggish hole. A truly advanced civilization might need to feed it fresh stars or gas clouds to maintain spin, a stellar-scale farming operation. Science fiction has flirted with these ideas for decades. In Alastair Reynolds' House of Suns, post-human cultures use black holes as timekeeping devices and energy reservoirs. The game Soma imagines a future where humanity uploads consciousness into machines powered by Penrose processes. Yet the most compelling thought isn't about technology, it's about survival. In a dying universe where stars burn out and matter decays, black holes will be the last structures standing. A civilization that masters them wouldn't just thrive, it could outlast entropy itself. Of course, we have no evidence such civilizations exist, but if they do, their signatures might be detectable. A black hole deliberately slowed by energy harvesting would have a distinct spin rate compared to wild ones. Oddly structured accretion disks or artificial satellites near event horizons could show up in future telescopes. Some even speculate that mysterious fast radio bursts, intense, unexplained cosmic signals, could be leakage from Penrose reactors billions of light years away. The irony is poetic. Black holes, often seen as nature's ultimate destroyers, might also be its greatest gift. They're not just endpoints, they're gateways to possibilities beyond our current physics, waiting for a species clever enough to crack them open. And if humanity ever reaches that level, we won't just be observing the cosmos, we'll be rewriting its rules. What if black holes have cosmic counterparts, not just pulling everything in, but violently spitting matter and energy back out? This is the tantalizing idea behind white holes, theoretical regions where time runs backward compared to their dark twins. While black holes trap light and matter behind an event horizon, white holes would theoretically repel them, erupting in outbursts so powerful they could outshine entire galaxies. The math allows it. Einstein's equations permit white hole solutions just as they do black holes, but the universe seems stubbornly reluctant to confirm their existence. That is, until a bizarre gamma ray burst in 2006 defied every conventional explanation, sparking whispers that we might have witnessed a white hole's death throes. The burst, labeled GRB 060614, was unlike anything astronomers had seen. Most gamma-ray bursts come in two flavors: short bursts from colliding neutron stars or long bursts from dying massive stars. This one fit neither, lasting just 102 seconds, far too brief for a supernova yet too long for a merger. It also lacked the afterglow that typically lingers for days. Even stranger, its energy signature resembled the theoretical, slow-roll emission predicted for white holes, as if space-time itself had hiccuped, briefly reversing the arrow of entropy. Some researchers proposed the unthinkable. What if this was a white hole, a relic from the early universe, finally evaporating in a final, spectacular pulse? The idea isn't as far-fetched as it sounds. If black holes form from collapsing stars, white holes could be their birth cries, moments where a black hole's formation in the past gets played backward due to extreme spacetime curvature. Picture a video of a vase shattering, then running the footage in reverse. That's the rough analogy for how a white hole might emerge from the equations. Quantum gravity theories even suggest that tiny primordial white holes could have formed in the universe's first instance, lingering like time capsules until their energy finally destabilized. But the skeptics strike back. For one, white holes violate thermodynamics by seemingly creating energy from nowhere. A true white hole would need a reservoir of pre-existing matter to eject, like a cosmic fountain with no hidden plumbing. Others argue JB 060614 could simply be a rare type of supernova or a neutron star with an unusually strong magnetic field, the most damning criticism. If white holes existed, we'd likely see more of them. The cosmos isn't shy about flaunting its extremes: quasars, pulsars, magnetars. So why hide hypothetical white holes? Yet the debate refuses to die. Some theorists propose a loophole. White holes might only exist briefly as black holes bounce during quantum transitions. Imagine a black hole collapsing to its smallest possible size, then rebounding like a compressed spring for an instant. It would behave like a white hole before vanishing entirely. If true, this could explain why we've only seen fleeting candidates like JB 060614. Others suggest white holes might be hiding in plain sight, their emissions blending into more common cosmic phenomena like fast radio bursts or unexplained X-ray flares. The truth might lie beyond our current physics. If white holes exist, they could be portals to understanding quantum gravity, offering glimpses of how spacetime behaves at the smallest scales. They might even be the secret architects of dark matter. Some models suggest certain types of primordial white holes could have decayed into exotic particles that now dominate the universe's mass. Until we catch one in the act, though, they remain the ultimate mirage, mathematically elegant, observationally elusive, and begging the question: are we staring at cosmic magic tricks or just misunderstanding the mirror? What if every supermassive black hole isn't just a dead end, but a doorway at the center of these cosmic monsters where gravity crushes matter into oblivion? The very fabric of spacetime might tear open, birthing entirely new universes. This isn't science fiction, it's a serious hypothesis from physicists like Lee Smolin, who proposed that black holes could be cosmic mothers, spawning fresh realities where the laws of physics mutate slightly each time. Imagine our universe as just one bubble in an infinite foam, each bubble inflated from the singularity of a black hole in some parent cosmos. The math behind this idea, dubbed cosmological natural selection, or the fecund universes theory, suggests that when matter collapses beyond the point of no return, the extreme conditions could trigger a quantum rebound. Instead of crushing into infinite density, the singularity might bounce, sparking a new Big Bang in a separate spacetime continuum. Picture a Russian nesting doll, but each layer contains an entirely new universe with tweaked physical constants. Black holes wouldn't just be destroyers, they'd be cosmic incubators, their violent deaths giving rise to new cosmic landscapes where gravity, light, and even time itself might behave differently. Evidence for this wild idea is unsurprisingly elusive but not non-existent. The fine-tuning of our universe's constants has long baffled scientists. Why is gravity just strong enough to hold galaxies together but weak enough to allow complex structures? Why do protons and electrons have precisely the charges they do? Smolin's theory offers an answer. Universes that produce more black holes reproduce more often, leading to a Darwinian selection favoring physics that maximizes black hole formation. Our universe's laws might simply be the ones that won the cosmic lottery by making stellar collapse as prolific as possible. Critics raise valid objections. For one, we can't observe other universes, making the hypothesis nearly untestable. Others argue that known physics doesn't permit information transfer between universes, so even if new ones form, they'd be forever cut off from their progenitors. Yet tantalizing clues linger. Some models of loop quantum gravity suggest singularities can't truly form. Instead, spacetime rebounds at ultra-high densities, echoing Smolin's vision. And if certain black hole mergers produce gravitational waves with unexpected echoes or resonances, it might hint at exotic physics operating behind the event horizon. The most mind-bending implication: if true, our entire universe could owe its existence to a black hole in some ancestor cosmos, a thought that twists the knife on humanity's cosmic humility. It would mean every quasar, every lurking giant like M87, isn't just a curiosity, it's a potential Big Bang in waiting, a universe to be. And somewhere, in some other reality, another civilization might be staring into their own black holes, wondering if they're staring back at us. For decades, the no-hair theorem stood as gospel in black hole physics, a deceptively simple idea that these cosmic vacuums could be described by just three properties: mass, spin, and charge. Everything else, the composition of swallowed stars, the quantum states of fallen atoms, even the screams of hypothetical astronauts, would be irretrievably erased, leaving behind a perfectly smooth, featureless event horizon. But a bombshell paper in 2022 shattered this orthodoxy, proposing that black holes might grow quantum hair, subtle structures encoding information in spacetime itself. This revelation doesn't just tweak the math, it threatens to upend our understanding of where information goes when it vanishes into the void. The roots of this revolution trace back to Stephen Hawking's original paradox. If black holes evaporate via Hawking radiation, and that radiation carries no information, then the universe's quantum rulebook, which insists information can never be destroyed, gets burned. The quantum hair solution offers an escape hatch. Imagine dunking a book into a black hole. According to traditional theory, the book's text is scrambled beyond recovery. But quantum hair suggests the book's ink might leave faint imprints on the black hole's gravitational field, like water clinging to a duck's feathers. These imprints wouldn't be the text itself, but complex quantum correlations between the black hole's interior and exterior, preserving information in a form we're only beginning to decipher. The breakthrough came from re-examining gravity's quantum behavior at event horizons. When matter crosses the point of no return, its gravitational field doesn't just switch off, it vibrates, creating what physicists call soft hair. These aren't literal strands, but infinitesimal distortions in spacetime that store data like a cosmic hard drive. Recent calculations show these fluctuations could encode the quantum states of infalling matter, with each new addition subtly altering the black hole's gravitational hairstyle. It's as if every swallowed star signs its name in the fabric of spacetime before vanishing. Critics aren't convinced. Some argue quantum hair conflicts with general relativity's smooth horizon predictions. Others counter that the information, while technically preserved, might be so scrambled it's effectively lost, like burning a library and claiming the smoke patterns contain all the book's contents. But proponents point to startling simulations where black holes with quantum hair evaporate differently than classical ones, leaving behind information-rich remnants. The implications stretch beyond theory. If black holes preserve information, they might not be the universe's ultimate shredders, but its most secure vaults locking away secrets we could one day learn to read. Future gravitational wave detectors might even spot these quantum hairstyles imprinted on spacetime ripples during black hole collisions. What began as a mathematical curiosity could end as the key to uniting gravity and quantum mechanics, proving that even in the darkest depths, nothing is ever truly forgotten. Before the Big Bang lit up our cosmos, before galaxies or stars or even time as we know it began, the universe might have birthed objects so strange they defy modern physics: dark stars. These hypothetical relics, first proposed by physicist John Michell in the 18th century, weren't stars at all, but gravitational traps so powerful even light couldn't escape. Today, we call them black holes, but what if some supermassive black holes lurking in galactic centers aren't products of collapsed stars or galactic mergers? What if they're primordial survivors, leftovers from a reality that existed before our own? The dark star hypothesis whispers a tantalizing possibility that certain black holes predate the Big Bang itself. In this scenario, these ancient anomalies didn't form from dying stars but from the collapse of ultra-dense regions in a previous cosmic cycle, a bounce from a contracting universe into our expanding one. Unlike black holes born from stellar collapse, these relics would carry no trace of heavy elements or accretion disks rich in stardust. They'd be pure gravitational pits, their event horizons pristine time capsules from an era before atoms. But could such primordial titans actually exist? Modern astrophysics sets brutal constraints. For one, the cosmic microwave background, the afterglow of the Big Bang, shows no obvious scars from pre-existing black holes. If dark stars were peppered across the early universe, their gravity would have distorted this radiation in ways we don't observe. Then there's the growth problem. Even if a few primordial black holes survived, they'd need to balloon to supermassive proportions without leaving evidence of their feeding frenzy. Current models struggle to explain how they'd gobble enough matter to reach billions of solar masses while leaving surrounding galaxies unscathed, yet intriguing exceptions persist. Take the quasar ULA's J1120 plus 0641, blazing just 770 million years after the Big Bang. Its black hole weighs 2 billion suns, too massive to have grown from stellar seeds in that time frame unless it started with a colossal head start. Could this be a dark star relic? Some theorists suggest these outliers might have formed in the violent instance of cosmic inflation, where quantum fluctuations could have birthed black holes directly from spacetime's stretching fabric. Others propose their evidence of exotic physics collisions between higher dimensional brains or vacuum bubbles in a multiverse. The darkest clue might lie in gravitational waves. If dark stars exist, their mergers would produce ripples in spacetime with unique frequencies lower and longer than those from stellar mass black holes. Future observatories like LISA could catch these echoes, distinguishing primordial monsters from their younger cousins. Until then, these cosmic elders remain ghosts in the data, taunting us with the possibility that some black holes aren't just inhabitants of the universe, they're its oldest living witnesses. At the heart of every galaxy, hidden behind the inscrutable veil of an event horizon, there might exist something far stranger than a simple cosmic vacuum, a natural supercomputer of staggering complexity. This isn't science fiction. Cutting-edge theories in quantum gravity suggest that supermassive black holes don't just consume information, they transform it, process it, even rewrite it in ways that could make them the universe's ultimate information processors. Imagine a cosmic control room where gravity, quantum mechanics, and thermodynamics collide to perform calculations so vast they dwarf every supercomputer ever built by humanity. The math behind this idea comes from holographic principle research. When matter falls into a black hole, its quantum information doesn't just vanish. It gets encoded onto the event horizon's two-dimensional surface, pixelated into Planck-scale bits. But here's the twist: that data isn't static. The horizon's extreme gravity and quantum fluctuations create a dynamic, chaotic system where information constantly interacts, much like transistors in a computer chip. Some physicists compare it to a quantum neural network, where the black hole's spin, charge, and mass act as adjustable parameters in a cosmic algorithm. One striking example is the AD/CFT correspondence, a theoretical framework suggesting that events inside a black hole can be perfectly mirrored by processes on its boundary, a duality akin to software running on hardware. The black hole's interior becomes the program, while the horizon acts as the screen displaying its output. This isn't just abstraction. In 2019, researchers calculated that even a modest black hole could perform more operations per second than all the computers on Earth combined across billions of years. But what does it compute? One radical proposal suggests black holes might optimize galactic evolution. Consider how quasars actively feeding supermassive black holes regulate star formation through their jets and outflows. Too many stars and the black hole's outbursts heat surrounding gas, stifling further star birth. Too few, and the lack of feedback allows cool gas to coalesce into new stars. This self-balancing act resembles a control system's feedback loop, fine-tuned to maintain equilibrium. Could this be computation in action, an unconscious universe-scale program running on spacetime itself? Another possibility, black holes as cosmic archivists. If information isn't destroyed but preserved holographically, these gravitational behemoths might store the universe's history in their quantum memory. Each swallowed star, each shredded planet, could contribute to a sprawling cosmic ledger, encoding the past in a format we don't yet understand. Some theorists even speculate that black hole mergers like the ones LIGO detects might be the universe's way of defragmenting this data, reorganizing information for optimal storage. The most mind-warping implication: if black holes compute, they might not just influence their host galaxies. They could participate in a larger universal network. Entangled black holes across the cosmos might exchange quantum information through wormholes or other exotic spacetime structures, creating a distributed processing system of unimaginable scale. It's the ultimate internet, a web woven not with fiber optics but with gravity and quantum entanglement, humming with calculations that shape reality itself. Of course, skeptics abound. Critics argue that calling black holes computers is just poetic metaphor, that their information processing is passive, not purposeful. Others point out that without a clear mechanism for output, the idea remains speculative. But as we peer deeper into the quantum gravity frontier, the line between physics and information theory blurs. Whether black holes are conscious machines or unconscious data centers, one thing's certain: they're far more than cosmic trash compactors. They might be the universe's oldest, most enigmatic programmers, running codes written in the language of spacetime. What if the universe isn't just aware, it's thinking? That provocative idea lies at the heart of one of the most controversial theories in modern physics: that consciousness itself might emerge from the quantum processes inside black holes. Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff proposed this radical notion called orchestrated objective reduction, ORC, suggesting that human consciousness originates from quantum computations happening in microtubules within brain cells. But here's the cosmic leap: they argue similar processes could occur in black holes, making these gravitational giants not just cosmic objects but potential seats of universal awareness. Penrose's theory hinges on quantum gravity, the elusive bridge between Einstein's relativity and quantum mechanics. In ORC, consciousness arises when quantum superpositions particles existing in multiple states simultaneously collapse in a structured, orchestrated way. These collapses aren't random, but somehow integrate information in a way that creates subjective experience. Now imagine scaling this up to a black hole, where spacetime itself undergoes quantum fluctuations near the event horizon. Could the same principles apply? Some theorists speculate that the extreme curvature of a black hole's interior might facilitate consciousness-scale quantum processes far beyond what's possible in human brains. The implications are staggering. If true, black holes wouldn't just be celestial phenomena, they'd be cosmic minds processing information in ways we can scarcely fathom. Picture Sagittarius, a star, not as a silent destroyer, but as an entity experiencing its own form of spacetime-altered awareness. This isn't fantasy. It's an extension of panpsychism, the philosophical view that consciousness is fundamental to the universe, not just a byproduct of brains. But let's separate speculation from science. Most physicists remain deeply skeptical. MIT's Max Tegmark famously calculated that quantum states in the brain would decohere, lose coherence far too quickly to support consciousness under known physics. Similarly, black holes' extreme environments would likely destroy any delicate quantum processes rather than nurture them. Yet Penrose counters that undiscovered quantum gravity effects, like those near singularities, might preserve coherence in ways our current models can't describe. It's a classic standoff between established physics and the tantalizing unknown. The debate intensifies when considering black hole information paradox solutions. If information isn't lost but preserved holographically on event horizons, could that preservation include the encoding of conscious experience? Some quantum mind theorists suggest that black holes might not just store information passively but process it actively, like a cosmic version of how our brains integrate sensory data into unified awareness. The problem: we have zero empirical evidence for such exotic consciousness mechanisms in black holes or elsewhere. Where does this leave us? Or remains firmly on the fringe, but it raises profound questions. Even if black holes aren't conscious, their extreme physics forces us to confront the nature of information, causality, and reality's deepest fabric, all themes that overlap with the mystery of consciousness itself. Until we crack quantum gravity or detect some signature of cosmic awareness, whatever that might look like, this conundrum will linger at the intersection of physics, philosophy, and sheer wonder. What's certain is that black holes continue to challenge not just our understanding of space, but the very nature of existence. Billions of years from now, long after the last stars have flickered out and galaxies drift apart into endless night, supermassive black holes will reign as the universe's final keepers of order. But even these cosmic titans aren't eternal. In a cosmos sliding toward heat death where entropy maximizes and energy spreads infinitely thin, their fate hinges on a battle between quantum decay, gravitational waves, and the bizarre possibility that they might become the last conscious entities in existence. Hawking radiation dooms them to a slow, cold demise. As space empties, black holes will no longer find stars or gas to feed on. Isolated and starving, they'll leak energy via quantum particles popping into existence at their event horizons, shrinking atom by atom over timescales that make the current age of the universe seem like a blink. A typical supermassive black hole might take 10 to the power of 100 years to fully evaporate, a 1 followed by 100 zeros. To grasp that scale, imagine every grain of sand on Earth counting down 1 trillion years. You still wouldn't be close. But the universe has stranger plans. As space expands, some black holes could be flung into the void so far apart that they never merge. Others might drift together in the darkness, drawn by gravity's unrelenting pull. When they collide, their mergers would send gravitational waves echoing through an otherwise silent cosmos, the last detectable ripples in a sea of nothingness. Then there's the wild card, Boltzmann brains. In an infinitely old universe, random quantum fluctuations could theoretically assemble self-aware structures from the sparse particles left. These disembodied consciousnesses would arise, flicker into existence, and vanish almost instantly. But supermassive black holes, with their immense gravity and Hawking radiation, might become the only environments where such fluctuations could concentrate enough energy to sustain them. It's a chilling thought that the last thinking beings in existence might not be civilizations, but rogue intelligences spawned by evaporating black holes in the void. Yet even this might not be the end. Some theories suggest that the vacuum energy fueling cosmic acceleration could spawn new black holes from quantum foam, ghosts of the old universe seeding the next. Others propose that in a multiverse scenario, our black holes could tunnel into other realities, becoming the dark seeds of alien cosmoses. One truth remains: supermassive black holes will outlast everything else: stars, planets, even protons. They'll stand as the final monuments to a universe that once teemed with light and life, silently bearing witness to the end of time itself. And when the last one winks out, the cosmos will settle into eternal quiet unless, of course, the cycle begins anew. From the moment a star is torn apart in a tidal disruption event to the mind-bending possibility that black holes could birth entire new universes, We've journeyed through 30 of the wildest, most inexplicable mysteries surrounding these cosmic monsters. Yet for every question answered, how jets blast matter at near light speed, why some black holes spin faster than others, dozens more remain shrouded in shadow. We still don't know how supermassive black holes grew so enormous so quickly in the early universe. We can't explain why they're eerily synchronized with their host galaxies. And we're only beginning to grasp whether they're cosmic destroyers or the architects of everything we see. Take frame dragging, the way spinning black holes twist time itself like taffy. Or the holographic principle, suggesting everything that falls in might be encoded on the event horizon in 2 dimensions. Then there's the haunting idea that dark energy, the force ripping the cosmos apart, could be tied to black holes growing in hidden ways. Each mystery peels back another layer, revealing how much we've yet to learn. Even our best theories crumble at the singularity, where gravity and quantum mechanics collide in a storm of unknowable physics. Now zoom out, picture the observable universe, a web of galaxies stretching 93 billion light-years across, each thread anchored by a supermassive black hole at its core. These aren't just oddities, they're the universe's gravitational engines, shaping everything from star formation to the fate of spacetime itself. Understanding them isn't just about solving puzzles, it's about decoding the story of existence. So, which mystery left you stunned? Was it the black holes that might be older than the Big Bang, the eerie quantum hairs preserving information, or the chilling chance that evaporating black holes could become the last conscious entities in a dying cosmos? Drop your thoughts below, because the more we explore, the clearer it becomes. The universe's greatest secrets are hiding in plain sight, written in